section 5.2, and before I show you the rest of the slides here, I want to introduce this in a slightly different way. Let's consider that what we've been looking at is an indefinite integral, such as the indefinite integral of x squared dx, and we have determined that to be x cubed divided by 3 plus c. There's a whole other definition for this, another way of visualizing this, and it has to do with if we were to graph this function, what would x squared look like? And so I'm going to graph this, and particularly I'm interested in from the input of 1 or 0 to the input of 1. And what I'd like to determine is what is this, the area between the curve and the input axis and then this right boundary of 1. Now, in order to determine this, what we could do would be to say, well, I'm just going to, we'll just make it into a rectangle here, and area is length times width. So area would be, if this is x squared, then this would be 1 also, so it'd be 1 times 1, or an area of 1 squared unit. Now, we can see that we have a lot of excess information here. And so what we are going to do then is to, instead of taking a rectangle such as this, we're going to choose more than one rectangle. And so if we take a look at this, we could look at, well, let's say we look at 2 rectangles. That means that we have a width of 1/2, and I come up here and my area, and then I would have these 2 rectangles, and the area of this rectangle would be 1/2 times 1/2 squared. The reason is that the height is dependent upon the point on the curve, and we put that up here. The function we're looking at, f of x, is x squared. So the area of this one would be 1/2 times 1/4, or 1/8, and the area of this one would be 1/2 also, but its height is now 1 squared, or 1, so it would be a height of 1, and so the total area would be 1/8 plus 1/2. Let's see, that's 1/8 plus 4/8, or 5/8 square unit. Our area that we've computed would be a little better of an estimation of the area just under the curve. Now, if we're going to look for a better estimate of the area, then if I take more rectangles, I would have less overreach here, and I could then estimate what the area is. Now, I'm going to be sending you and giving you this program, but for right now, let's just look at it. If we have this curve, now this is a slightly different curve than what we were talking about. Just one second. I'm going to go back and change this this so that it is the same one. Just one. Okay, so here's the graph we were looking at, y equals x squared, from 0 to 1, and we have our 2 rectangles, and the approximation of those areas is 0.625. If we take 5/8 and convert it into a decimal, it is 0.625. We were saying that if we could increase the number of rectangles, so I'm going to increase the number of rectangles, and again, this is a program I will give to you, but let's say that we double the number of rectangles, so I'm going to use 4 here, and let me try that one more time. So if we use 4 rectangles, our area is approximately 0.47. If we continue to use more and more rectangles, so let me go in here and change it. Let's say instead of 4, we use 8. We are getting less area above the curve that is excess area, and we're getting closer to the actual area. Now, the question is, how many of these can I use before I have an exact value, or as close to an exact value as possible? Well, let's see. If we try 16, we would have, let me put that in again, 16. We would have then an area of about 0.365. You know, the question is that close enough? Well, as I work with this, I hope you're thinking that of the fact that we're using a limit. As the number of rectangles approaches infinity, what is happening to the area of the total area of all the rectangles? So I'll put 32 in here. And we keep getting an area that is going, getting down, as getting lower. But how low can it actually go? And so we'll do one more of these. And just as we would do with some others, we could get pretty crazy here. And instead of 32, maybe 320 or so. Now, there gets to be a problem with using the Inspired, where it sometimes will take a little bit of time. As wonderful as a computer as it is, it will take a little bit of time. But let's just see if 320 kind of overloads it. It doesn't overload it, but you can see that we have 320 of those rectangles, and our area is getting closer and closer. So to 0.33. So we could imagine that if we use infinitely many rectangles, our area seems to be approaching 0.33. Now, a question that some of you might be thinking of is, well, what if instead of using rectangles that are going to be above, what could we use some that actually are below? In other words, let me get this set up for us here, and we'll take a look. I'll show you what I mean by that. What if we have rectangles whose height is not dependent upon the left endpoint, but rather on the right endpoint of each of these intervals here? Now, in order to talk that language to you, let me go back over here and illustrate that information a little better. We're talking about, on these, we were using what we would consider to be the right endpoint of each of these sub-intervals. So each of my rectangles has the same base, but the height of the rectangle is dependent upon the right endpoint of the interval. So we went up to the curve on the right. Over here, we go to the right side of that and go all the way up. When we are looking at the rectangles that are using the left endpoint, this one really has an area of 0 because we're using the left endpoint of this interval. Over here for this rectangle, I use the left endpoint to determine the height. What would happen if we were to use more than 2 rectangles for this, using the right endpoint? What if I use, well, we'll jump to 16 right now. And now what happens is I have areas below the curve and between that and the rectangles that's not being used in my calculation of area. So now I'm going to be underestimating the area, but I'm going to do what I did before. We'll just jump to our 320 though. And if I am increasing, again, the number of rectangles, the amount that I'm not going to be using is going to be minimized greatly. And if you remember, we had about 0.33 square unit for that area. Now, what we're about in this section is to come up with some way of adding up all the areas of the rectangles. And to do that, we have to use some information called the summation information. Let me go back to the very front here. Sigma, some of you know that symbol from the fraternity organizations. Sigma is stands for the summing up of multiple units, and so this would be the summation as the index I ranges from 1 to n. This tells me how many items I'm going to add up, and I would add them up, and this would be then the sum. We have what we call the index of summation. Again, I goes ranging from 1 to n. The ith term of the sum is designated as a sub I. Upper and lower bounds, in this case, go from 1 to n. And we have some properties of summations. Now, again, you've seen these before. This one is saying that if I'm going to add up n terms, and I have then all of that summing up multiplied by a scalar, that scalar, k in this case, can be then brought to the outside of the summation, and we can add up all those terms and then multiply it by the scalar. This one says that if I'm summing up, if I have the sum or difference of two different terms that I'm adding up, it's the sum or difference of the summations. Again, you've seen those before. They keep occurring in our work. These are just then some shortcuts. These are again those patterns that some people have observed, some mathematicians have observed, and they are showing us that instead of having to do this longhand, we can just use these summation shortcuts. For example, if we have a problem, let's say the index goes from 1 to 3, so that means I'm going to have 3 terms, and C stands for a constant. And let's say the constant is 2, it means that I want 3 of these very same things. I'm going to add them together, 2 plus 2 plus 2. That would be the same thing as taking 2 times how many units or how many terms? 3 of them, and we would have then 6. So if you have the summation of a constant, it's the constant value times the number of units that your terms you're going to be adding together. Now, this one I know you've seen before. You probably studied it probably in Algebra 1. Carl Friedrich Gauss was the young mathematician who came up with this, and he was given the task in school of adding up all the numbers from 1 to 100. So if we just take a look at this piece right here, and we use Carl Friedrich Gauss's problem that he was given, he was asked to add up 1 plus 2 plus 3 all the way up to plus 98 plus 99 plus 100. Now, a way to write that is to use our summation symbol, and we're going to go from an index of 1 to 100. And we're going to just use the index I, and that means that whenever the first time through, the first term is going to be the first value of I, which is 1. I go through it again, and I have then the next index would be 2, the next one would be 3, and so forth, and I keep adding those until I get to 100. Carl Friedrich Gauss looked at that problem he was given, and he thought, well, if I'm adding up 1 plus 2 plus 3 plus 4 plus 5 up to 98 plus 99 plus 100. Well, you know, if I take that very same set of numbers I'm adding up, but I instead add down from 100, so 100 plus 99 plus 98 plus 97 plus 96 plus 3 plus 2 plus 1. Now let's see, if I add those all up and I just add down on each of these, I get 101, 101, 101, 101, and in fact every single sum I'm looking at is 101. Well, he was thrilled to know that he could do this. However, when he thought about it, it was how many hundreds and ones? Well, he had 100 101s, so that would have been, though, the sum of 2 series here. And so he said, well, you know, really, I only need half of that, so he divided by 2 and came up with the fact that